Welcome to the online causal inference seminar. Today, we are excited to have Jonas Peters from the University of Copenhagen. He will speak about causality and distribution generalization. He will speak about several projects. We have many collaborators today. We have Stefan Bauer, Peter Bühlmann, Rune Christiansen, Nicola Gniecko, Martin Jakobsen, Nicola Meinshausen, Niklas Pfister, and myself. Niklas Pfister is also with us today in Q&A and will help us answer questions that you have. Jonas will also stop from time to time to take questions from the audience. After Jonas's talk, we have a discussion by Yuansi Chen from ETH Zürich. And then if we have some more time, we will take some more questions from the audience. All right, thanks for joining. And I will now switch over to Guillaume, who's handling the questions.
Thanks, Dominic. So the Q&A will work as usual. Today, we're lucky to have Niklas, who will be answering your questions. So please do not hesitate to ask them. We will select a few questions to ask directly to Jonas. So the way this will work is I will select some of the questions and reach out to you to ask you if you're comfortable asking them live. If you are, I will ask you to raise your hand. So please, again, don't raise your hand unless I've asked you to do so. All right, that's pretty much it on our end. Jonas, feel free to start whenever you're ready.
Thanks a lot. Thanks a lot, Dominic and Guillaume, for the introduction, and thanks a lot to the organizers for the invitation. So let me see whether I can share the screen now. Okay, so I hope that you can see the presentation now. I'm going to talk about causality and distribution generalization. And as Dominic already said, this is far from being a complete story. I will present a couple of key ideas, and hopefully they nevertheless make up an interesting story. So let's see. These are the collaborators that you have heard about now with pictures. Stefan, Peter, Rune, Nicola, Martin, Nikolai, Niklas, and Dominic. Also, I am particularly happy that Niklas, who is really an expert on all of the things I'm going to talk about, is helping with the questions. Okay, so what is the setup I would like to consider in this talk? So we are given a response variable y and some covariates, let's say x1 to xd, and we have a training distribution. So think about model M, and then the training data is just IID data from this observational distribution. Now, what is the thing that we would like to analyze? So we are looking for a prediction model. So think about f hat of x that performs well, not only on this training model, but also on test data which may come from a different distribution. So this is, of course, a well-studied problem. It has many connections to existing fields in statistics and machine learning, domain generalization, out of distribution prediction, covariate shift, and so on. So the problem we are considering in this talk has the following form. So we are looking at the minimax problem. So what do I mean by this? We are starting with the model M. And now we are looking at a risk, so a prediction error. That's what you can see here on the right-hand side, the expectation of y minus f squared of x squared. And now the point is that we are not only looking at the training distribution, but we are looking at the neighborhood around the training distribution. So these are all models M tilde in n of m. So this is the neighborhood around m. And now we're looking at the sort of the worst case tests that we can have, and now we are trying to minimize this. So we are in some sense we are interested in the model that is minimizing the worst case risk here. Now this is of course also a well-studied problem, and often you see that the neighborhoods are chosen with respect to a certain metric. So let's say in Wasserstein distance. Now in our talk we would like to take a bit of a different approach and look at intervention distributions, as we are going to see in a second. But first, to make sure that we're on the same page. So imagine for a second that this neighborhood is trivial. So it only contains the model M. Then, of course, we are back to the if you like, ordinary least squares problem. So we are just looking to minimize the mean squared error in the training distribution. And they are a classical thing that we would learn in statistics 101, like OLS regression would be the right answer. So how is causality related to this at all? So if you look at a causal model, and what I mean by this, so imagine, for example, that the variables really come from a causal model, like a structural causal model. And then a causal model would only consider the direct causes of Y, let's say. So these can be some of the covariates. So how is this related to this problem? Well, it is well known that if you consider a lot of intervention distributions, so all interventions on the covariates, and take the supremum over these distributions, then the causal model is actually minimax. So this is what's written here. So it looks more complicated than this. So it's well known that the causal model satisfies that it's actually the minimizer, it's included in our function class, of this optimization problem, where we are now looking at expectations of these M of I. So these are interventions that we actually obtain when we intervene on some of the covariates or on all of them. So if we are looking of the set of interventions that are really all possible interventions on X, then the causal model is the minimax solution here. So this is, of course, well known. Let's just look at this from a data perspective. So this is a data set that we have been looking at already a couple of years back. This is genetic data from yeast. It's the Cameron data set. And here you see an example of a non-causal model. So you have a target or response Y on the Y-axis, and you have another gene, a covariate X. So what you see here are activities of the genes, and you see that there's a strong dependence. So you could say that if you just regress Y on X, you find maybe a linear model you can try out, and this seems to be working quite well. But if I now look at a test distribution that is really different, and here if I look at the test distribution where I intervene on the gene on the x-axis, then this model may actually perform quite badly. And this is what you see on the right-hand side. So this is one additional data point from this test distribution. The biologists have intervened on this gene on the x-axis, and you see that the linear model that worked well in the left-hand plot doesn't work very well in the right-hand plot anymore. And this is the problem with non-causal models. It's intuitively hopefully clear, because imagine, for example, that you are including a child of your response variable, then this is of course helpful for the prediction, but if you intervene on it, then of course your model may give arbitrarily bad answers. Now in contrast, if you're looking at a causal model, so this is now another pair of genes, what you see here, but here, if you're now asking the same question, well, if you're fitting on the training data set on this causal model, then actually in this particular case, it also performs well on an interventional data set, where we, again, this additional data point is from an intervention distribution where the biologists have intervened on this gene on the x-axis. Now, of course, it's another question whether a linear function is really the best thing here to do, but hopefully the idea comes across. And now this is a bit of a question now. Of course, in reality, we don't know what the causal function is. So the question is, how can we find it from real data? And there are, of course, a lot of different methods that one could use. I'm not going to talk about all of them, but I will instead focus just on one idea that is at the basis of instrumental variable regression, and also at something that we have looked at over the last years, and many others have. And this is the idea of invariance. So where does it come from? It is based on the following idea. So if the data really come from two different, let's say, environments, so you see this now on this plot, it's orange data and blue data, then you can argue, well, if this should be a candidate model for a causal model, then because of the just said reasons, it should work well under both of these different distributions. So in particular, it should be invariant if the environments, let's say, are constructed by interventions that are not on the target variable. And here you see that this is actually indeed a candidate for a causal model, because if you imagine putting a regression line through the data set on the left, through the orange and the blue one, then it actually seems to work fine in both of these data sets. Now, how can you quantify this? So how can we measure sort of whether we have an invariant model or not? So there are, of course, many ideas how to do this. I'm going to focus on one that we are using later as well. And this is just shown in this picture here. So this is now a model that is non-invariant. So you have the response on the y-axis, and you have one covariate on the x-axis. This is not an invariant model, which we can see by just looking at it, right? So the orange data seems to be generated by a very different model than the blue data. But how can we measure this? This is in one of the ideas that you can say really comes from this instrumental variable approach, or that are exploited by many other methods as well, is to say, well, you can just pool the data, the blue and the orange data, and fit one joint regression. The result is what you see here. This is the black line. And now you can check whether there is a correlation between the residuals and the variable that is indicating in which environment we are. So this is here indicated by an A equals 1 and A equals -1. And we are now just checking, is there a correlation between the residuals and this environment variable? And here there is. So this correlation is non-zero. And again, this hopefully makes sense, because if you look at the picture, you see that in the orange environment, the residuals tend to be more negative than in the blue environment. And this on the right-hand side is very close to what is often called the two-stage least squares or IV loss function. So this really comes from the instrumental variable regression. And the point is that here, this A, you can think of this being the instrument. This has the idea of being exogenous. Now, this is one way of trying to search for causal models, and so to maybe give a high-level idea here. So I've just argued that when you're only interested in sort of the training distribution and performing well in the training distribution, then you can just focus on prediction. This is what we're doing in OLS. But if you're interested in finding a model that sort of works relatively well also under all sorts of interventions, then you should really focus on invariance, because this might yield a causal model. So of course, I'm aware that I was a bit vague on the details here, but hopefully these two different loss functions, we're going to see them in a second again, they give a meaning. Now, of course, the question is, well, what happens if we do something in between? So we have seen that in the prediction, we are only sort of protecting ourselves against the training distribution. When we only focus on invariance, we may hope to get a causal function. This is protecting ourselves against arbitrary interventions. What happens in between? And in a particular setup that we're discussing in a second, we are going to see that indeed there will be a trade-off. So we can find models that protect us against some interventions of a certain strength, but not of arbitrary strength. And this is what can be made formal in a linear setup with what we call Anker regression. So this is what the A stands for. And again, to remind you of the setup, so we have a response Y, we have some predictors X, and we have some instruments or anchors A that we assume to be normalized. And then how do we make this trade-off mathematical? Well, we're just writing down a loss function like this. So the first term, the orange term, this is the prediction. So y minus xb squared, this is the mean squared error. And on the right-hand side, you see the term that we just saw a second ago. This is, if you like, a measure for non-invariance. So of course, we can have more than just one instrument. So we are taking the norm here on the right. And now the gamma, this is something like the knob that you can turn to specify the trade-off. And if we are minimizing this, this is just what we call the Anker regression coefficient. Now, just to make sure that we're on the same page, so if you put it to 0, we are just back to OLS. This is a predictive model. If we are turning the knob to the other side, going to infinity, then we are just focusing on the on minimizing the right-hand side, the right term, so this green part, and you actually end up with a solution that is very close to two-stage least squares, but that, for example, also works if you don't have identifiability. But the big question is now, well, what happens if you have gamma in between? And this is now the result that I just mentioned. So you can show that you are sort of you obtain a solution that is actually minimax. The interventions that you're looking at are not of arbitrary strength. So let me make this more concrete. This is looking at a linear structural causal model. So what do we see here in the top? This is just the SCM, if you like, the covariates X, the target Y, and then some hidden variables H. And this is a linear structural causal model. And now you can think of A being the exogenous variable that enters the system. And now we are looking at interventions. What kind of interventions? We're intervening on A. So let's call this model M of delta. So delta is now the intervention index here. And we are just setting this variable A to delta. So this gives us a whole new bunch of distributions. So these are the intervention distributions. And then what is the result? The result says that indeed this Anker regression coefficient, this is a minimax solution. So it minimizes the worst case prediction error. And now worst cases over all these interventions that we consider up to a certain strength. So the strength is now encoded in the C gamma. So this depends on gamma. And this is just one way of writing it. So we just allow for a delta with a certain norm. And the larger, of course, the gamma, the more interventions we are protecting ourselves against, but also the closer we come to the two-stage least squares solution. So this is one of the, so one concrete example where you see a minimax solution that is not the causal solution. How does it look like in practice? Well, in practice, of course, we are not looking at population means, but just we replace all of these terms with finite sample properties. And then it really boils down to quadratic functions that we are minimizing. So this is now a scenario for a specific data set. Here we have a two-dimensional vector. So B1 that you see on the x-axis and B2 on the y-axis. And the red lines that you see, these are now the level sets of the OLS loss function. So if you just minimize the OLS, you would find this red dot as a minimizer. But now we have the second term. This is the, if you like, the invariance term. This is indicated by the green lines here. These are, again, level sets. And here, if you would look at the two-stage least squares solution, then this is the solution that you would get. And Anker regression now finds this trade-off. So what you end up with a solution that is on this path. So you are in some sense interpolating between the two-stage least squares and the OLS solution, but of course it's not a straight line necessarily. So now what I try to argue here is that this is one way of trading off, sort of finding models that may extrapolate well in a scenario that we observe in practice, where maybe we want to perform well on a test set, but we don't believe that the interventions are arbitrarily strong. There's now one more aspect that I would like to add, and this is really now a bit of an excursion, and I hope it doesn't add too much confusion. And the reason is that there's another motivation for looking at estimators like this that come from a bit of an orthogonal direction. And this is looking at finite sample properties. Because it's a bit of an orthogonal direction, I will put the background in yellow. So you will see that these yellow slides, when you come back to the white slides again, so if you like, you can forget about everything on the yellow slides and still follow with the remainder of the talk. So what do I want to say? Anker regression can be motivated by improved finite sample properties too. And this is hopefully intuitive. So if we are looking for a causal solution, then in some sense, these two-stage least square solutions are not the optimal thing to look at. Why? Because they look at in some sense, a correlation between the residuals and the instruments. But they are putting them to 0. And this, in some sense, this is too harsh, because even for the true solution, you would expect that the sample correlation is small, but not necessarily 0. And then what we can do is we can just, if you like, regularize by looking at including the OLS objective function. And this is an idea that exists. So the Anker regression estimator is can be shown to be a K-class estimator. And this has been looked at already a couple of decades ago. And here the motivation is to improve the finite sample properties of, let's say, a causal estimate. Effects in a just identified setup, for example, the two-stage least squares doesn't even have finite moments. So you can really improve the finite sample properties there. And to add a bit of an intuition, if you come from that angle, you can also ask, well, what is the optimal gamma that I can set? But if you're coming from this direction, there's a very intuitive way of setting this. This is an alternative, if you like, to Lindell and Fuller. So the intuition is to say, well, we just look at all solutions that yield uncorrelatedness between the residuals and the instrument. And among those, we choose the one that is best in OLS. And this would mean that you're choosing a gamma such that, and this is now a bit of an ad hoc idea, you're choosing the gamma such that if you then test for a correlation between the instruments or anchors and the residuals, you get a p-value of exactly 5%. So this means that I'm saying, okay, I'm interested in invariance, but among all these invariant solutions, I'm choosing the one with minimal OLS. So you can show that you can actually solve this. So this is the same picture as before with the green lines and the red lines. And now, in addition, what you see here, this is this blue area. This is now the acceptance region. So these are all the solutions such that we would not reject a test for uncorrelatedness. And now, if you use this idea that we call pulse, then you would choose this black dot. So this is among all the ones that are sort of not rejected, that are in the acceptance region, we choose the one with the smallest OLS. And this is just coming from a very different angle, but hopefully it makes sense that you can already see that by this idea you can improve the finite sample properties. Here this is a non-convex region, but it's actually still a simple optimization problem that can be solved very efficiently. And also, not surprisingly, it's sort of asymptotically you're doing the same thing. It's really about the finite sample size. So in an identifiable setting, you are you're consistently estimating the causal parameter. Okay, this was a bit of the excursion. So far, we have looked at only linear models. And now there are two questions, of course, that come to mind. The first one, is this ever useful? Because we are looking at linear models. And the second one is, can we also extend this to nonlinear models? And this is where I would like to take the first break and see whether there are any questions.
Thanks, Jonas. So a quick question. You've given an interpretation for Anker regression if the model is correctly specified. Do you have like, is there still an interpretation if under misspecification?
Yeah, thanks. This is a very good question. I'll come back to this in a second or a bit later in the talk, if I may. Okay.
Yeah. Perfect. Yeah. Yeah. And yeah, that's pretty much all that we have so far.
Okay. So there are two sort of things I would like to talk about today. And the first one is whether this is ever useful in practice. And I would like to show you one case study that we did where the data looks a bit different, but we're using the same idea. Oops. And this is how it looks like. So this is a chemical reaction network. It's known as the Maillard reaction. So what are the ingredients? So these are a lot of amino acids and sugars. And what you see here is a differential equation. So the GLU, this stands for glucose. The parenthesis is a concentration. So we are looking at the concentration of glucose at time t. And now this changes over time, and the rate depends on a lot of parameters, for example, also again, the concentration of glucose and so on. And as you have already seen, maybe on the next slide, this is a very well-known reaction that all of us know. This is one way of visualizing it. So this is an example of a raclette. So some cheese in front of the fire, and you see on the bottom of the cheese, you see that it gets brown. So this is this crust, and this brown thing, gives the nice flavor. This is melanoidin. This is actually the outcome of this reaction here. Now, why is this a data science problem? The Maillard reaction is quite well understood, but a lot of other reactions of this type are not well understood. And the question is whether you can learn it from data. So how do the data look like? You could measure these so-called species over time at discrete time points. And you can measure several species represented by these three plots. And maybe you have repetitions of the experiment. And then the question is, can you somehow infer the network structure from the data? This is a very well-studied problem. There's a lot of methods that have been proposed. I'm not citing all of them here. Something I'm not going into details here. I skip this. That is often used as nonlinear least squares, where you actually solve a lot of numerical ODE systems when producing your estimator. However, we approached this problem from a bit of a different angle, and we wanted to see whether these invariance principles can also help here. So this is a very high-level picture of the method. So again, we observe the data in different experiments. So let's say green, red, and blue, and we have again our response Y, and we have a lot of covariates. And now we're interested in finding a model that sort of extrapolates well, in the sense that it would also work well on a unseen data set that is maybe represented here by this yellow experiment. Now, again, what you could use, you can say you just focus on prediction, pool the data, and just look for the the model that fits best. But you can also, and this is what we tried, you can also try to incorporate this idea that says, well, if you have a model that fits well overall, but that predicts very badly on one of these environments, the blue one, this is probably not the best idea if you want to have a model that transfers to an unseen experiment. And this is where we came up with a method where basically you're again trading off predictability and invariance, where you're saying, well, in two sentences, so you smooth the Y's. This gives you some derivatives. You can then regress them on the covariates for a given model. And then you can check, well, if I now just use the other experiments and use the information that I get from the other experiments and plug them into my model. So I put them in as constraints, saying, well, the other models really think my derivative should be that, like -1 at this point. I put them as constraints into another smoother, and then I can just check how badly I fit on this, let's say, green experiment. The idea being that if there's an invariant model that performs well in all experiments, then this should really not hurt at all. Whereas if the model changes between the models, then incorporating the information of the model from the other experiments should really be a bad fit. So anyways, what you get out is you get a criterion that takes into account both predictability and invariance, and you can use this for ranking models. So this might be the highest ranked model. So out of all the covariates that you have, you think this is performing well in terms of predictability and invariance. And what was a bit surprising to us, or to me at least, is that this performs relatively well on this real data set that we looked at. This is metabolics, where we have about 400 covariates. We have 5 experimental conditions and 3 repetitions. And I just show you maybe the resulting model. So this doesn't say as much, right? So there's a huge model class. This is a model that was spit out by the method. But maybe a bit more interesting is to look at the plots. So what do we see here? This is the response variable over time. And the green curve is the fit from our model. And then at the same time, you see also this blue curve. This is just a smoother. And this we see now for different methods. So here on the right-hand side, these are sort of state-of-the-art methods. The yellow and the red one, where the red one is we chose to underfit the data a bit. So maybe also, what are these little red lines that you see on the smoother? At the end of the day, we are building a model for the dynamics, right? So we thought that it would be nice to evaluate also the model on how well it predicts the dynamics, not only the data themselves. So this is what the model predicts in terms of a derivative at this point. So you see here that this is an in-sample plot, so there's not a big difference. So maybe you can even argue that the yellow one looks a tiny bit better than the green one. This is the causal kinetics one that we propose. But if you now look at out-of-sample experiments, the picture changes a bit. So here you see that first you see it's a very difficult problem. So this first experiment, for example, this is now where we show the results for if you hold out this experiment, you train on the other experiments, and then you just see, well, what does my model or method predict on this experiment? And you see that this is a much harder task now. So none of the methods is perfect, I would say, but it seems to be that this causal kinetics seems to capture a bit more of the dynamics. And now there are a couple of things to say here. So one, and I would like to stress this, is that here, so of course we are trying to, we were trying to find a method that takes into account this invariance, and the reasoning is that if your model doesn't even generalize on the 3 data sets you have seen in your training time, then it's very hard to believe that it generalizes well to the test data. So we incorporated this explicitly. So this might be one reason why the performance here is a tiny bit better than for other methods. However, and now I'm coming back to this yellow story, I believe, and here I think it's fair to say that we don't understand the details, at least I don't. So we believe that there's also another interpretation, namely that you are regularizing in some sense, you're regularizing with non-invariance. And this, I think, is an important point, in particular in these type of models where the classical way of regularizing, let's say in lasso or ridge penalty, wouldn't work because these covariates are somewhat not, they don't necessarily live on the same scale, and you cannot normalize them because of the type of the model. So these type of regularizations that we're used to wouldn't work here, I think, whereas you can also see, this is the yellow story, maybe this is another way of regularizing these models. And to which extent these two things also sort of support each other, this is something that I think still needs to be understood. Okay, so this is another short break. If there are any further questions.
Yeah, so one quick question by Dominic, actually, and then we'll let you continue because we don't have much time left. Dominic?
Yeah, thanks. Just in that application, so it seems you had 5 experiments in total, or how many? Did you? So did you try a bit and see how many training experiments you need until you get good out of experiment performance? So do you need 2 environments, 3 environments to train 4?
No, here we used 4, and I think this was also important in particular because you see, for example, that you have 2 downshifts in experiment 1 and 2. So if you leave them out, I think it's very hard to correctly estimate the downshift. Okay. So indeed, this is of course a question, a very good question. How many environments do we need? And I think theoretically we don't have an answer to this. Here, practically, as you can see, this is trained on 4 now, predicting the 5th, right? And it's still not perfect.
Okay, great, thanks.
There's one more aspect to the story, and this is, I think that's now also a bit clearer to me than it was maybe half a year ago. And this is that these models also are linear, right? So they're linear in their parameters. And this is important for extrapolations, as we're going to see in a minute, because here we have to extrapolate, because if you are using sort of, let's say you're fitting a model in 2 environments, and you're trying to test it on a 3rd environment, then often your covariates will take values in areas that you haven't seen before. Therefore, you need to extrapolate. And this is, of course, you can do very well with linear models. This now sort of brings me to the last point. And this is a bit of an experiment. So because the question is, well, can we do something with nonlinear models as well? And here, I'm trying to introduce a framework that we use to analyze this question a bit. And I'm not saying that this is a perfect framework, but let's see. I would be more than happy to receive input on this because for us, it's also rather fresh. I should also say that this is really a group effort. So I'm now presenting this work, but could be anyone else from the group as well. So how do we tackle this question? So we are starting again with a structured causal model that looks like this. And we really use this now. Maybe don't think too much about a causal ground truth, but we are using this for generating intervention distributions. So we have our response y, our covariates x, we have a hidden variable h, and some exogenous variable a. It doesn't have to be there. And now we are looking at the noise variables, and they are jointly independent, but they can have dependent components. Now, what we are now modeling are interventions, and we are starting with the model M. So this is specified by all these different functions here. And we are saying that we are considering interventions, and they yield a model M of I. And now it turns out that for the analysis, there are actually two types of interventions that play a crucial role. The first one we call confounding preserving. So what does this mean? This looks now terrible, but the idea is simple. So it means that actually the influence of the hidden variable on the x is sort of maintained the same. So here you see that this is really a function of h2 of h epsilon x. And this is the term that also appears in the original SCM. So if this remains the same, we call this a confounding preserving intervention. And the other one that is important is confounding removing. So if after the intervention on x, the h really doesn't have an influence anymore. So think about a hard intervention setting x to a random variable that is independent of the rest or something, then this would be confounding removing. And then the target of inference that we would like to analyze is again this minimax solution. So again, here we are now looking at a potential minimizer of the supremum over all intervention distributions of the risk. And now, so I'm trying to present some of the results, and I'm aware that they can be a bit technical. I try to explain everything. This is the last thing that I want to do today. So the first observation is that it's well known that sort of under all interventions on X, the causal function is the minimax solution. But it's actually, there's a much stronger statement, namely that it suffices if you only have one confounding removing intervention. Already then the causal function is minimax. And this is just written in this proposition. So if you consider a set of interventions and at least one of them is confounding removing, then F is minimax. There are many interesting analyses that you can do. But there's one thing why we thought that maybe this is not the optimal framework yet. Why? Because in reality, we, of course, again, we don't know what the causal function is. We are only given the observational distribution. So we tried to develop a framework that takes that into account. And therefore, we have to modify the definition a tiny bit. So this is the observations. And practice, the minimax solution needs to be identifiable from Pn, so observational distribution. And this motivates the following definition. So we are saying the observational distribution Pm and the model class M is said to generalize to I, to the interventions. Forget about the epsilon for a second. If there exists a function f star that is minimax, and now that is important, that is minimax for all models M tilde that have the same observational distribution. So the important part is that, of course, if we never know whether we are in model M or M tilde, if they have the same observational distribution, so we would like the F star to be minimax for all of them. And now the epsilon just means well, it also suffices if it's approximately minimax, because the minimax solution may not exist. And this is written here. So we have that this model generalizes to I if there exists a function f star, such that for all models m tilde with the same observational distribution, we are approximately minimax. And this is this is what we call distribution generalization. And now this is the framework that we can use for answering some of these questions about theoretical limits. And this is just a slide summarizing some of the results that I would just like to propose, and maybe they yield some discussion. Let's see. So this is the assignment that we're looking at. G of A, f of x. So this f is the causal function here. And we said that we looked at different interventions. So confounding preserving means basically that the influence of the hidden is not changed. Confounding removing just crosses out this link between x and h. And well behaved is now meaning that we have a set of only confounding preserving or at least one confounding removing intervention. Now there are some assumptions that I skip. I come back to them in a second. And now we can sort of fill out the following table. So we can now try to analyze under which assumptions it's possible to have distribution generalization. And it turns out that a very important point is to consider the supremum, the support of the covariates under the interventions. So if the support of the x doesn't change much in the sense that we call this support reducing, so you're not trying to generate x values that are very different from what you have seen before, then you have distribution generalization under a quite general setup. This is assumption here, A1 is just identifiability of your function f. Think about an IV setup where you have sufficiently many instruments that allow you to identify the causal function. But, and now this is sort of the key point, if you're also interested in intervention distributions where the support is what we call support extending, so the support is now not contained in the original support anymore that you have seen, then you really need much stronger assumptions. Namely, this is A2, this is the extrapolation of f. And this basically means if you know it on the support, you know it everywhere. And this is of course satisfied for linear functions. So this is what we have seen in Anker regression as well, and we have seen also in the ODE setup in some sense. This is also true for other function classes, but linear ones come, of course, to mind the first. And this is, you also have negative results. So without this extrapolation, in general, you cannot expect to have distribution generalization. And then sort of the same holds if I have interventions on A. I'm aware of the time, so I will stop soon. So you can do the same analysis now for interventions on A. Why? Because they are sort of reducing to confounding preserving interventions in some sense. And again, you have now A3 is just, again, the same conditions for F now for G, so identifiability and extrapolation. And sort of you have similar results. And the last one also says that if you intervene on A, and again, you have support extending, you really need to have the extrapolation property of your function G. And this last row is in some sense, I consider it as bad news for nonlinear versions of Anker regression. Because if, and it hopefully makes sense, in Anker regression, we are really trying to extrapolate. But now if we have arbitrary nonlinear functions, this extrapolation is just not possible. So I thought it's always bad to end on a bad news, and therefore I wanted to talk a tiny bit about the second row, which actually allows us to have a positive result as well, right? So it means that if we have a nonlinear IV setup, for example, where we have identifiability of the nonlinear function, and now we also have an extrapolation property. So you can think about nonlinear functions that extrapolate linearly. So this is an extrapolation function class. Then you can actually achieve distribution generalization. And this is something that at least we haven't seen before. So we developed our own methods for this. And this is should really be seen as a proof of concept that this works. So in a nonlinear IV setting, you can generate models that generalize. So this is what we call NILE, nonlinear intervention robust linear extrapolator. And these are just, this is the last slide, these are just hopefully making sense intuitively. So if you look at the middle plot, you see some data for y and x. This is the black data. You see the true function, this is the green function. And now if you just do something like OLS, you will get a biased solution because it's an IV setup. And if you just do nonlinear IV, you get something that doesn't extrapolate. But if you're constraining yourself to this function classes, then indeed you can construct something where this distribution generalization is possible. But again, the strong assumption is that you can extrapolate outside your support. Good, and with this, I would like to conclude. I skip the experiments here. So this is, these are some of the points that I try to raise. So these causal models, one way of looking at them is well known, of course, is that they are minimax solutions, and you can actually prove that they are already minimax under small intervention classes. And then Anker regression, this is it can be seen as one sort of different minimax solution in linear models. We looked a bit at extending this principle to real-world data sets in these chemical reaction networks. And then the last way is really an attempt to maybe start with a theoretical framework that allows us to answer some of these theoretical questions of what we can expect to work, and maybe identifying some scenarios where we don't even have to look for methods because they're theoretically impossible to solve. Good. With this, thanks a lot for your patience, and I stop here.
Great. Thanks, Jonas, for the very nice talk. We're now switching over to the discussion. We will have Yuansi, Chen present some slides, and then Jonas will have an opportunity to also respond. Yuansi, you can start whenever you're ready. But you should also unmute yourself. You're currently muted, I think.
Sorry. Can you see my slides, Dominic?
Yes, we can see your slides.
Okay. Okay. Hi, everyone. This is Yuansi. Sorry, maybe I should share this way. So I would like to thank Jonas for the wonderful talk first. And I would like to thank organizers for inviting me to be a discussant on this online causal inference seminar. It's an honor to discuss the papers from Jonas. And I've been learning a lot from this online causal inference seminar. Thank you for the organization. So a little bit background of myself. I'm right now a postdoc with Peter Buhlmann at ETH Zurich. So my PhD was not on causal inference. I started to get familiar with the causal inference literature about 1 year ago when I started to learn the causal inference when I start my postdoc. So I apologize if some of my opinions are biased. So talking about biased opinion, I used to think causal inference was about very important decisions we make about epidemiological studies, economic policy, and public policy making. And as we have seen in this seminar theory from Elizabeth Tipton's talk, it's about educational experiments. Or from Susan Murphy's talk, is about how to make decisions to lose weight smartly. I used to think it was also about debunking mysterious commercials about chocolates and cigarettes. Well, it's not very clear here whether Peter is trying to debunk the myths or trying to promote his favorite chocolate brand, given the big logo here. But so these are very important questions in causal inference. But for someone like me, who's come from machine learning background, who actually does not have much interest in politics. Causal inference was not an exciting field, but it turns out I was quite naive. And reading actually Jonas' papers and some papers from his co-authors, actually, it made me more and more convinced that actually causal inference is very important topic for people in machine learning, or people who only, even for people who are only interested in prediction problems. So the particular scenario where causality comes in is when actually the training and test distributions are different, and you need a framework to formulate this type of problems. And this is a field that is well studied, and people come up with different ways to formulate the problem, like the domain generalization, domain adaptation, covariate shift, or transfer learning. It's a good sign that so many names come up, because currently there's no dominant framework to frame the problem precisely. So I would like to congratulate Jonas for making this excellent talk. And he provides actually a framework to think about the problem where the training and test data sets are from different distributions. So some summary of the talk: he first made the causal estimator an interesting estimator, even for prediction problems. And then he introduced a range of estimators between the causal and the least square estimator by looking at what he showed is like a trade-off between the prediction and invariance. This little button you can tune between the prediction and invariance. And he has convincing examples to show how it works and how to choose hyperparameters. And also he also discussed like very difficult problems when you want to extend to nonlinear cases. So of course, there's a lot of work covered in this talk. I will not be able to cover all the problems. I'll just discuss a few points that I find interesting. So the first is I try to show a very simple example so that we are in the same page, so that we can make the following discussion easier. So the data generation formulation, domain generation formulation typically begins with the case where the training data distribution and the test data distribution is the same. Right, then you can start to think about how the training test data distribution can be different from the training data distribution. And then there's a famous line of work, distributional robustness or adversarial training, where you think about the test data distribution is slightly perturbed compared to the training data distribution. And you can think about this as an example where in computer vision problems, the classifiers need to be robust to small noise added to the images. So this is an important line of research. Actually, the current line of like using causal inference for domain generalization is beyond that. Actually, it's trying to cover the case where the test data distribution is even far from the training data distribution. So there are two important ideas actually from Jonas' papers that made this possible. Because this is a very difficult problem, because you can imagine the test data, when the test data and the training data does not share support, you can imagine the function, the ground truth function might be a linear function here and maybe a quadratic function in the test data, and you have no clue about it. So it's very difficult, but it's possible when you incorporate these two important ideas. The data structure, your data usually has structure. It's not just from IID, from normal distribution with covariance matrix identity. It has some structure, and the structural equation model is one way to describe the structure in your data. And also, you have multiple sets of training data, what they call the multiple invariants as well. So by observing multiple sets of training data or multiple environments, you might get a clue of where the test data might be coming from. And so here is a very simple problem, very simple data generating model. You first generate X, then you generate Y, then generate X2. and noise is just the normal 0, 1. And you can compute the causal estimator and OLS estimator. They're actually different. The causal estimator, obviously for this data set, is not going to be good for prediction, because the OLS estimator for this data set will have the best mean square error. But when does the causal estimator becomes useful? It's when you kind to perturb your model, when try to have an intervention on the data generator model for X2. And so here I just show simple simulations where you add more and more intervention and you still compute to the OLS estimator. So when you add the OLS, you perturb the data generator model by amount 1, 5, and 10, and you can compute the OLS solution. The OLS solution is always changing when you perturb the structural equation more and more. And when the perturbation is large enough, the OLS solution actually corresponds to the causal solution. So what does that mean? So if you just care about your green data set, then you don't need to, for prediction problem, you don't need to talk about causal estimator. But if you anticipate that your test data is going to be perturbed in some way, and for example, in this way, and then the causal estimator actually, even though does not have the best prediction performance in the green data set, but has actually good performance in the in the red data set. So so basically the anticipation, whether you anticipation about the test data becomes important. So this leads to the main question I have actually. In practice, you want to have some information about the test data to be able to apply this framework, because according to the Anker regression formulation, you want to assume that all the data sets, data distribution come from this type of model. And if the test data is not generated exactly from this model, you have trouble. For example, in this simple, in this example, if you don't know anything about the test data distribution, you might be training this estimator that is robust to the training data here. Like each is one of the, each blob is one of the training data cloud. And if the training data is very limited, and you might be training again, training your model to be invariant across this training in the X2 direction, but if your test data set is here, you are not going to be robust against this kind of perturbation in the X3 direction. Will not have any. So the Anker regression will have difficulty to have guarantees. On the other hand, so one way to deal with this is to assume that the source, the training data set has some kind of heterogeneity. So when the training data set has some kind of heterogeneity, the way Anker regression is stated is the minimax solution. So when, in the sense that it's anticipate that test data cloud can come anywhere among the convex set of the training data distributions. But here's another problem when you actually have many heterogeneous source data training data environments, is that if you happen to have some information about your test data distribution, it is close to one of the training data distribution, but it's not anywhere in the data cloud of the training data distribution. Then using the Anker regression or pulse or this type of minimax estimator might not be the optimal estimator in terms of the prediction task. Here you might want to actually just use the training data set number 4 and try to run an Anker regression or using the training data set that's close to a test data set. So that will lead to my question that actually when we are not sure about the test data generation, is there any guarantee for Anker regression on the test data model specification? And can we actually test this test data model specification. For example, we are given a little number of test data points, like 10 test data points. They're not enough to train a data model directly on the test data, but are they enough actually to tell you that you should or should not apply Anker regression? As the second point is related. So basically, ideally you want a training data set, many training environments that is heterogeneous enough that the test data distribution is covered in its convex set. But if you have too many training data sets, then you might train some estimator that is too robust, that might not have the best prediction performance for your test data. So how in practice we should think about this trade-off? Okay, I'll leave the mic to Dominic.
Fantastic. Thanks, Yuansi, for the discussion. Jonas.
Thanks a lot. These were excellent points. I think the time is almost over. I try to keep it very short. I think these are very good comments, and to many of those, I simply agree. So this also comes back to one of the questions I think Guillaume asked earlier, this robustness. So often these many-max solutions that are not the causal solution, you can actually prove that they are non-robust, in general, non-robust with respect to misspecifications of the interventions. And this is also true for Anker regression in the sense that if you misspecify, so in reality, you actually see interventions that were not in the class of your intervention model, then you can actually obtain performances that are worse again than the causal model. So I fully agree. It's a tricky issue. So therefore, I also think it's a tiny bit more skeptical how much we can actually gain in relation to the causal model. But I think this was an excellent point. And then the other one I just want to mention again, I think if we come back to it, and this is what we try to give a bit of a theoretical framework, it's really about the extrapolation that becomes important if Anker regression should do something. And this, I think, is indeed a tricky point, because if you have non-linearities, for example, you can in general not expect this extrapolation anymore. And the last point, how to choose the gamma. I think this is, I fully agree. I don't think there's an answer to this. There's a bit of an answer if you're really trying to find the causal model, I think. But still, I would do the point. In reality, I mean, this is what sort of was important for me to see, for us, I think, with this causal kinetics. It seems to be that there could be something gained. So this was the example where I thought, okay, it seems like this is just working better than other methods. But again, the analysis is, I regarded the theory, the final sample guarantees, I regard as an open question. So in short, thanks a lot. Very interesting points.
All right. Fantastic. Thanks. I think it's now time to wrap up. First, let's thank everyone who was involved today. Jonas for the great talk, Yuansi for a fantastic discussion, also Niklas for rocking Q&A and answering all the questions. Next Tuesday, we have Eitan Bakshi from Facebook Core Data Science. We're very much looking forward to that talk. Again, thank you all for coming, and hope to see you all next week. And please stay safe. Thank you.